Okay, so I think we'll make a start now. Welcome everyone to this Methods Hub seminar series on Should We Abolish Statistical Significance? My name is Tarani Chandola. I'm the director of the Methods Hub here at the University of Hong Kong. And I'm delighted that we have Dr. Peter Martin talking to us today about this topic. So Peter is an associate professor in biostatistics and psychological methods at University College London. He obtained his DPhil from the University of London in 2010 and joined UCL as a lecturer in applied statistics in 2017, and then was promoted to associate professor just a couple of years ago. And Peter is most well known for his work on a range of statistical issues, particularly on life course research and optimal matching, as well as mental health research. And he, on top of that, he's written 2 books for SAGE on regression modeling. So this is somebody who can tell us about the hot topic on, statistical significance. He's definitely somebody that can talk to us about this topic. So I'm just delighted that he can talk to us today. So whenever you're ready, Peter, please go ahead.
Well, thanks very much, Tarani, for the nice introduction and for inviting me to give this seminar. Very pleased to be here. I've never been in Hong Kong physically, but I hope to be one day. And so good afternoon, everyone. So I think it's usual in this meeting that the speaker speaks for about 40 minutes. So that's what I'll aim for. And then there'll be plenty of time for questions at the end. Feel free to put your questions in the chat as we go along, or later on once I've finished speaking. You can also unmute yourself and we can have a discussion. So again, thanks for inviting me. And here we go. Should we abolish statistical significance? So I'm going to give this talk in 6 parts. I'm assuming that everyone here has heard of statistical hypothesis tests before and knows what they are. But in part 1, anyway, I'm going to do a very brief recap by example of what's probably the first statistical hypothesis test in history, which also introduces some of the issues with hypothesis tests, I would argue. Then in part 2, I'm going to introduce the debate about p-values and why some people now disagree with their use, or at least advise caution with use of p-values. In part 3, I'm going to link this topic of statistical hypothesis tests and p-values to the wider issue of what's been called the replication crisis. So the difficulties that have been found in many disciplines of replicating results that have been published and been taken as firm results, as firm findings. In part 4, then I'm going to explain more about how these topics, replication crisis and statistical hypothesis tests, are linked in 3 cautionary tales, so very concrete examples of what can go wrong if you trust your significance tests too naively. And in part 5, I'm going to get into more detail about how this belief in statistical significance, the way it's currently being used anyway, sometimes causes false findings being published and believed. In part 6, I'm going to talk about what can we do to make things better. So that's it. So we start with the first statistical hypothesis test. I'm speaking to you from Scotland, so it's kind of fortuitous that the first statistical hypothesis test probably was done by a Scottish person, and John Arbuthnot, who was one of these people in the 17th, early 18th century who were still able to dabble in all the sciences as far as they were known at that time. So he was kind of a polymath. And among other things that he did, he also conducted the first ever statistical hypothesis test. So he was interested in birth statistics. So this was the time when cities and states first collected statistics about their populations. For example, it's about how many people died in a year, how many people were born in a year. So he got interested in birth statistics, and he looked at the birth statistics in London. And at the time he was doing that, he had 82 years of birth statistics available to him. And he noticed that in each of these 82 years, the number of boys born was larger than the number of girls born. So he started thinking about that. And he then conducted the following test. So he thought, well, if we assume that the male-female birth ratio was 1-to-1, so that on average, a child is as likely to be born a boy as a girl, or that on average, the number of boys and the number of girls born should be equal. Then if we make that assumption, then the probability of there being 82 years in a row where there were more boys than girls would be quite small. So in a particular year, you'd have the probability of there being more boys than girls would be a half. But for that to happen 82 times, the probability of that would be a half to the power of 82. That was his rationale. And that probability is really small. So this is what today we call a p-value. He didn't call it that. And this hypothesis that he started from, the assumption that he started from, the male-female birth ratio is 1-to-1. That's what we today call the null hypothesis. So he said, if I assume the null hypothesis, the probability of me observing more boys than girls in 82 consecutive years is very small. Therefore, we can reject the initial hypothesis. Under that hypothesis, the data that we see are so unlikely that the hypothesis must be wrong. And that's still the logic of statistical hypothesis tests today. And his conclusion is also interesting. So he concluded that, and what follows from that is that it's art, not chance, that governs. It's quite similar to what people today say when, how people today sometimes say, describe the tests, the result of hypothesis tests, when they say it's unlikely that this result came about by chance. So it's got he's using a very similar formulation. But what he was actually interested in, like many European scientists of his time who were Christians, he thought that science is really has the purpose of discovering the plan of God. And so he believed that there's a Christian God who intervenes in the world to put into effect a divine plan. And so he thought, well, that this fact that he had uncovered, that babies are more likely to be born boys than girls, is evidence for a divine plan, because boys and young men are more likely to die before they can marry than girls and young women. It's because boys tend to have more accidents. They get drawn into more dangerous occupations, and they get drafted into wars. So more of them die before they can marry. But, and that was his Arbuthnot's argument, there should be, God should arrange it so that there should be one man for every woman. And so his theory was divine intervention compensates for boys and young men being more likely to die by adjusting the sex ratio at birth so that more boys are born, so that at the end there should be one man for every woman. So today we still often do statistical significance tests in a very similar ways. And some of the shortcomings are also similar. So For example, I would say that Arbuthnot's test was useful. It uncovered a new aspect of the world at the time, and it does address an interesting question, but it does also fails to answer many other interesting questions. So, for example, if you have a theory that more boys are born to so that to adjust for boys dying from accidents before they can marry, could you not, instead of having this null hypothesis of, well, boys are equal, number of boys equal to number of girls, you could have a specific hypothesis from your theory to predict specifically how many more boys than girls do you expect to be born. You could also think about, should this sex ratio at birth actually change in times of war, when more young men die before they can marry and have children, than in times of peace, when that's maybe less likely. So he didn't use his theory to predict specifically what he expected to see. He just used the generic null hypothesis that he didn't believe in order to reject it. Second, he didn't consider alternative explanations for his findings. So his finding still stands. The sex ratio at birth is today estimated as about 1.05, so about 105 boys born to every 100 girls. But of course, today we have alternative explanations. It might be something to do with evolution, for example. But Arbuthnot didn't consider alternative explanations. He thought, because he's rejected his null hypothesis, that he had evidence for his particular theory. And today we think, well, that's not the case. You can explain this fact in different ways. He also didn't use his data to estimate the male-female birth ratio, which is actually an interesting statistic, and it can be used to in various ways in science, for example, to check whether in particular cultures or countries or periods of time there may have been sex-specific abortion, for example, or even infanticide. So it's actually an important statistic to know what is the male-female birth ratio, rather than just saying we know that it's not 1-to-1. So the point is, the statistical significance test that he conducted was useful, but there's a lot of other things you could do that it fails to do. So to have a finding like, well, the null hypothesis is very unlikely. Well, it's unlikely to have brought about, if the null hypothesis was true, our data are unlikely to have been observed. That should be the start of an investigation, not the end. So the small p-value is not the end of our investigation, it's the start. So what about p-values then? By whom and why are they being criticized? So first of all, in 2019, the American Statistician, as the journal of the American Statistical Association, published a large special issue with over 50 articles, all about all arguing essentially we need to move to a world beyond just dividing evidence into p is either smaller than 0.05 or p is larger than 0.05. And not all of these articles, but some actually argued we should abandon statistical significance altogether. Not necessarily p-values themselves, but this binary decision criterion: either our result is statistically significant when the p-value is small enough, or it's not statistically significant. There was one psychology journal already in 2015 which went further and said we're going to ban p-values altogether. This is the Journal of Basic and Applied Social Psychology, and so if you submitted an article to as manuscript to this journal and it contained a p-value, they would send it back to you and say, well, we'd be happy to consider it, but you need to remove all the p-values. And then interestingly, so that made the scientific news at the time. But interesting, when Nature, one of the foremost journals of science in the world, wrote about this, they actually had to publish a correction later on, because they misdefined what the p-value is. Originally, they said the closer to 0 the p-value gets, the greater the chance the null hypothesis is false. And that's a fundamental misconception about what the p-value tells you. So the p-value is not a probability about the null hypothesis. The p-value can only be calculated if you assume that the null hypothesis is true. So the p-value doesn't give you the probability for any hypothesis. So that's it's in fact one of the fundamental misunderstandings that many people have. And it's one of the critiques also of the p-value, in that it sort of seems to encourage that misunderstanding and doesn't actually give the scientist what they want. A scientist would like to have the probability of a certain theory being correct or not, but that's not what the p-value gives you. The p-value gives you the probability of seeing the data that you did see under the assumption of a certain hypothesis. That's called the null hypothesis. So this goes to demonstrate some of the issues with significance tests and p-values today. There are many common misunderstandings that don't only appear when you ask people to define tests, but also appear in practice in the way p-values are reported in published scientific papers and statistical significance tests are used. So just to mention some of the practically most sort of relevant, I think, or sort of stark misunderstandings. So there's a confusion between statistical significance and scientific importance. You hear that quite a lot when people talk about their results. They believe that if the p-value is small, that's an important result in terms of, for example, if you study medicine or health research, that it makes a difference to patients, and that is not the same thing. A small p-value, especially when it's smaller than 5%, is often mistakenly interpreted as proof of an effect. So we have a statistical significance. We now know that we have a finding. We now know that this is the truth about the world. Conversely, and maybe even more frequently, a large p-value is mistakenly interpreted often as proof of absence of an effect. And that is definitely not the case. So I see quite a lot of publications that say, for example, there was no correlation between X and Y. Actually, there was a correlation in the data. It might have been even quite large. Just it happened to have a large p-value associated with it. Such a result doesn't mean that there's no correlation. It just means you don't have strong evidence to suggest that there is one, but absence of evidence doesn't necessarily mean you've got evidence of absence. It's also often mistakenly assumed that the null hypothesis always has to specify no effect or no difference or zero correlations. You can in fact do hypothesis tests about all kinds of hypotheses, including null hypotheses that specify, for example, certain sizes of effects. And lastly, and I'm going to talk about that more later, there's also a failure to recognize the conditions under which p-values are valid in the first place as indicators of the strength of statistical evidence for or against some hypothesis. So I'm going to return to these issues, but I'm going to kind of make a second start and talk about this other debate, which is the crisis of replication. It's often called the replication crisis in science. And I mean, there are several sort of important sources of the debate, but one important one was this paper here in 2005 by John Ioannidis, who argued that many published research findings in medicine and health research are false. And there are a variety of reasons for that, but one of the reasons he identified is research teams in chase of statistical significance that publish evidence, publish results as firm findings when they're really statistically quite poorly supported. And since that paper, there have been efforts in many different scientific disciplines to check, to take high quality, studies from high quality journals, selections of studies, and try to replicate them. So by replication, I mean usually just do the same study again with a new sample, but using the same methods as the original study. So this has happened in psychology, social science, preclinical cancer research, and also in several subfields of epidemiology and public health and medicine. In all of these, and some of these were quite large-scale efforts. The psychology one, I think, was over 100 papers, if I remember right, that they were trying to replicate. And overall, they found that there's quite a high proportion of published results that if you did a new study using the same methods, you couldn't confirm the original finding. So, and also the average effect sizes that were found in the replication studies were on average were a lot smaller than in the original studies. Another problem that was unearthed in this sort of tradition is that sometimes the published manuscripts didn't even contain enough information for, sorry, I got confused by the recording message. Another issue that these replication programs unearthed is that many published manuscripts didn't even contain enough information to replicate the methods from the original studies. So there's also, these replication projects also unearthed the problem with open science, scientific accountability, and proper documentation of your methods. So this could be quite, so you could consider this to be quite worrying in the sense that we have scientific findings being published, and it turns out when you check them that many of them are wrong. So you could say, well, should we stop trusting science then? But the counter argument is that actually things being published and being checked and then found to be wrong, this is not a problem of science. This is part of science. This is exactly how science should work. There should be debate. There should be checks and balances. There should be several people investigating the same question, coming to different conclusions, and then discuss why. So replication and failure of replication is the business of science. It's not in itself a problem in science. The problem is, of course, if you think that one published study with a small p-value already tells you what the truth is. Maybe the replication crisis could serve as a reminder of the importance of replication rather than as a cause for worry that science is inherently broken. So I'll illustrate the importance of replications in 3 cautionary tales using particular studies. So the first one is this: it's about power poses. So in the front here you see Amy Cuddy, who is a academic psychologist who did a study on power poses. In the back you see Wonder Woman from a Hollywood film. So Amy Cuddy and her colleagues did a study on power poses where they it was a psychological experiment, and the participants in the experiment were randomized, and so half of them were instructed to hold a power pose for 2 minutes. And by power pose they mean a physical pose that projects power and confidence. So it would be something like sitting on a on a chair with your feet on your desk and your arms sort of relaxed behind your head. That would be an example of a power pose. And then the control conditions, so the other participants were instructed to hold what they called a submissive pose. So this would be something like hunching yourself up, looking down, making yourself small. And so they found in their original experiment that holding a power pose for 2 minutes resulted in higher testosterone levels, among other things, compared to holding a submissive pose. And the p-value for that testosterone result was 0.045. Just also note that this was a really small experiment. It's only 42 people. And as a result of that study, Amy Cuddy then promoted power poses as a way to boost performance. She did a TED talk, which at one point was one of the most popular TED talks of them all, and wrote a book on it and so forth. And then people started to do replications because there were several, let's say there were several psychologists, quite a lot, who said, well, this is it's an interesting finding, but it doesn't really tally with other theories we have about how the mind and the body work together. And so there were many replication studies, and by 2017 there were enough of them to do a review of them, and they concluded that overall, after having done about a dozen studies or so, that there was no evidence at all for an effect of power posing on testosterone, although some evidence of a power pose increasing your self-reported feelings of power, so your subjective confidence. But that was sort of ambiguous evidence and not a big effect. So none of the replication studies found an effect of testosterone. So what's the problem here? The problem was not that the initial study was a badly conducted study. It was a well-conducted study, although there are always methodological arguments you can have, and there are publications that summarize those also. So the main mistake, I would argue, was to take the results from this small study as established fact and then build a big theory on that fact without checking it, first of all. So this is an example of what they call a type 1 error, I think, probably, in that you found a small p-value potentially by bad luck, in a sense, because in truth, holding a power pose doesn't influence testosterone. Nonetheless, by chance, as they say, a small p-value was found, and the mistake was to trust that and to say, oh, this is now an established truth. Now, the first tale was about having too much confidence in what a small p-value might tell you. The second tale is about having too much confidence about what a large p-value might tell you. So I don't know if you've seen this kind of graphs before. This is a typical graph that is made to summarize results from a meta-analysis. So we have here displayed risk ratios with confidence intervals, and the risk ratio is the risk of dying from cardiovascular disease if you do exercise after you have after recovering from coronary heart disease, or versus if you don't exercise. So risk ratio of 1, which is this line here, would mean there is no effect of exercise on your risk of death, and risk ratio smaller than 1 would indicate that exercise has a positive effect because it reduces the risk of death. So there are 8 studies, which I've called here A, B, C, and so forth, sorted from kind of smallest to largest. And the smallest study is here, so it had a risk ratio. This square here indicates the risk ratio that the study found was 0.71, and these lines indicate the confidence interval. So you notice that there are 8 studies. Each of them found a risk ratio smaller than 1, but for all of them, the confidence interval includes the value 1, which is to say all of the studies had a p-value larger than 0.05 for the null hypothesis that exercise has no effect. So if you have done your individual study and you found that, you would have the correct way to report the result would have been, well, our p-value was quite large, therefore we can't claim that we have strong evidence for an effect of exercise. What some people take it to mean, of course, is our p-value was large, so there is no effect of exercise on risk of death, which is a subtle but actually importantly different thing. Because if you look at these 8 studies, if you now look at all 8 studies individually, each of them would have found no evidence for an effect. But if you do a meta-analysis and you consider these 8 studies together, kind of pooling the results from them, you actually find that there is strong evidence for an effect if you from the 8 studies together. In fact, the estimated risk ratio is 0.56, and this is the confidence interval, about 0.4 to about 0.8. So it could, the data actually point to a reduction of risk by potentially almost 50%, or say between 24 and 58%. So that's a considerable reduction in the risk of death. So exercise does seem to be good for you in these circumstances. So trusting your large p-value and saying, well, our study shows that there's no effect would be quite wrong, because each study individually is too limited to actually show that. And then cautionary tale 3, this is about trusting a particular type of study, and trusting the p-value from that study too much, as opposed to considering other indicators of the strength of the evidence that you have. So there was in the 1990s a strong tradition of many observational studies, so studies of medical records without any randomization, that found an association between vitamin C intake and the risk of various diseases, including heart disease. Many of these studies found that vitamin C was protecting you from heart diseases and in some cases other diseases. But of course, we know that observational studies always suffer from the fact that no randomization is involved. So you can never rule out the possibility that your finding might have been influenced by unobserved confounders that you didn't control for in your analyses. Nonetheless, because the results of the observational studies were so seductive, maybe partly because their p-values were all quite small, this association between vitamin C and heart disease became accepted as an established fact. But when a randomized controlled trial was done to look at the effect of vitamin C intake versus not, it was found that there was no evidence for an effect at all. So in this case, trusting the p-value from a particular research design that has weaknesses over actually considering those weaknesses in the original design systematically has led to a misleading summary of the strength of the evidence. So these are cautionary tales, but more systematically, does the current use of this concept of statistical significance in research cause the publication of false results? And I would argue, yes, sometimes it does. So if you focus on p-values as the main or the only measure of the strength of the evidence for a finding, you risk ignoring many other factors that should be considered. So prior evidence from other studies, the plausibility of the mechanism you're proposing. So, so how plausible is it that holding a pose for 2 minutes would raise testosterone. If it's a priori not very plausible, you should be even more cautious of claiming a finding, especially even if you have a small p-value. The strength of the study design and the quality of the data, all those things, the p-value doesn't take account of in itself, but they're often forgotten about when the focus is on, oh, the p-value is small, therefore we have strong evidence. So these things are also often treated as subordinate factors, but they should actually be at least as important as the p-value itself and as measures of the strength of the evidence your study has produced. And there's also systematic misuse of statistical hypothesis tests in research in many fields of science, I would argue. So I'll go through them quite quickly because I realize I've been talking a bit slower or maybe in more detail than I intended. So I'm getting close to what should be my finish time. I'm going to slightly overrun if that's okay, but I might speed up my run through these 4 issues that are all about ways in which hypothesis tests currently are misused in many fields of research. So there are publication bias, multiple testing, fishing for statistical significance, and researcher degrees of freedom. So first of all, publication bias. So, I mean, this is well known. I might not tell you anything new here, but many academic journals prefer to publish articles that present surprising findings, and things that have a small p-value often seem to be more surprising and novel than things that don't have a small p-value. So if editors select articles for publications that have a small p-value, then and the studies that potentially study the same question have a large p-value don't get published, then in the published record, you only ever see small p-values reported. So it looks like there's strong evidence for a particular finding, but that's only because all the papers with null findings never got published. And it might not just be that journal editors have rejected them. It might be that researchers self-censor and they say, well, it's not worth writing up a manuscript with a large p-value because it won't get published anyway, and it's not exciting and it won't be interesting. So I rather focus on the things that have small p-values. But if you do it that way, you create, or well, if science works that way, then a bias is created in the published record. So the evidence looks stronger than it is, and also the effect sizes look larger than in reality they are. Now, multiple tests and selective reporting is also a frequent problem that has many aspects, but especially if a study design allows you or involves you doing many statistical hypothesis tests, but then you only report, but then you focus in your interpretation or even in your reporting only on the ones that yielded statistical significance, failing to report or discuss the ones that didn't, you will probably be largely overstating the strength of the evidence that you actually have. So a very stark example of that was this study here, where researchers in neuroscience went to the market, to a fish market where somebody sold fish intended to cook, and they bought a dead fish and put the dead fish in an MRI scanner. And then they showed this dead fish pictures of human faces that had different sorts of emotions. Some were emotionally expressive and some were emotionally bland. And then they analyzed the data from the MRI scanner in the usual way that many neuroscience experiments would do. And they found a statistically significant finding whereby the dead fish can understand human emotions. And of course, they didn't believe that this was true. They did this whole study in order to show that the study design the analytic design didn't adjust properly for multiple testing, because what you do in fMRI studies, you study like small regions of the brain. They're called voxels, so small three-dimensional areas, essentially little cubes. And for each of them, you're checking, is there a difference between, when we showed the dead fish, the picture with the expressive faces versus the not expressive faces. And so if you study a sufficiently large number of voxels, sooner or later you get a small p-value that is just small by chance, rather than indicating a real difference. Because in these fMRI data, there's lots of noise, lots of things, so you don't always get the same reading, even if you read the same thing twice. So you're just picking up the noise rather than a real effect. So this study was done to demonstrate to neuroscientists that their current methods for correcting multiple comparisons were not sufficient. Then fishing for statistical significance. If you can do something similar to the multiple comparisons fallacy, and actually improve your publication record if you design your study cleverly. So if you conduct a study that has, say, many outcomes and many possible risk factors or things you want to associate with the outcomes, you could analyze this large data set, test many different hypotheses, and then select the ones that have small p-values that are statistically significant for publication, and write your research report as if you had hypothesized this finding from the beginning. So this is called p-value hacking or harking, hypothesizing after the results are known. There was a journalist who did this intentionally to show that eating chocolate helps you with weight loss. So he had he actually did a proper study. He randomized people into eating dark chocolate, milk chocolate, and no chocolate. But then he had, I think it was 20 different outcomes. And so by chance, the chocolate eaters had more weight loss than the non-chocolate eaters. But apart from weight loss, they had 19 other outcomes that he was checking. And then he reported this study. He made a press release for this study and saw what happens, and it got reported in media all over the world. He then later revealed it as a spoof, he wanted to show how easily media report poor research. For what I want to show is it's how easily it is for someone to actually systematically abuse this property of the p-value, is that it's only valid if you hypothesized, if you had the hypothesis before you collected the data and did the test. If you select your results by the p-value, the p-value has no meaning because it doesn't really tell you what you wanted to tell you. You're just picking up statistical noise. And then finally, you can also, this trap, this p-value, this fishing for significance strategy, people can also fall into the trap of using that inadvertently. So they're trying to be good scientists, but they inadvertently actually conduct multiple tests and then in the end up trusting the one that has a small p-value. This has been called researcher degrees of freedom, and the next slide illustrates that. So it's also been called the garden of walking paths, because in the course of an analysis in many scientific fields, you have multiple decisions to make. There are potentially some outliers. Do you exclude them from the analysis? Yes or no? You might have missing values. Do you impute missing values? Yes or no? Maybe you should analyze the data in subgroups. Maybe older people should analyze older people and younger people separately, or men and women separately, or people from different cities separately. So if you make all these decisions, all these decisions, you might do the analysis two ways just to see what happens. But if you have many decisions to make, in the end, you might end up with quite a large number of different analyses. And it's quite easy to then convince yourself that the one that shows the thing or seems to show the thing that you'd like to see is the one that you should trust. So for example, people might say like there was no correlation between X and Y among men, but there was one among women, so that's important. And then they report that result. But actually, you have inadvertently done multiple tests and you found a small p-value just because you would have found one sooner or later if you do the analysis in sufficiently many different ways. So the trouble here is again to select your results by the p-value and to trust the p-value over other measures of the strength of the evidence. For example, plausibility of a finding. Did you have this theory before you started, and so forth. And I'm gonna I've said what this slide says, but just to say, just to emphasize this point. So the p-value is only a valid indicator of the strength of statistical evidence if it relates to a hypothesis that you specified before seeing the data. I mean, ideally, and that is what you have to do in clinical trials, you need to say how you will analyze your data before you have the data. Of course, in some social science studies, when you do secondary analysis, that's not practically feasible, but you need to be aware that then the p-values you get, if you already select certain analyses by what's, how big some differences are, how big p-values are, you need to be aware that the p-value is essentially meaningless as a measure of the strength of the evidence. And I'm going to skip this slide in the interest of time and come to what can we do. So if you do your own analysis, the p-value that you get from your statistical software of choice looks scientific, but it may be entirely meaningless because it depends on how you've conducted your study and analysis. When you read published research, it's not always possible to tell how meaningful the reported p-values are if they don't tell you exactly how they've done the analysis, and if they haven't pre-specified the analysis, often you don't actually know how meaningful the p-value is. Misinterpretation of p-values is common, both when people talk about it and when they write about it. I think over-reliance on hypothesis tests is harmful to science, and even if the p-value itself, I would say, is a measure of statistical evidence for a hypothesis under the conditions I've laid out, but to dichotomize the strength of evidence into either it's significant or not, that's often misleading. I think it can be useful in some contexts. For example, drug regulation, do you approve the drug or not? You need some sort of cutoff point. But much of science isn't done in terms of either this is true or not true. It's done about the slow accumulation of evidence. So even a study that has a large p-value adds something to the body of evidence, and a study that has a small p-value isn't definitive. So why should we dichotomize by cutting p-values in these two categories, either smaller or larger than 5%? There have been many proposed solutions to some of the problems I've laid out, and they are, I don't think they all apply in the same way to all scientific fields, but I think they're interesting to consider. So one solution is more emphasis on estimation, such as confidence intervals. It has been called the new statistics by some people, but it's actually very old statistics. It just reverses this sort of myopic focus on p-values that has developed in some fields of research, maybe especially psychology. More emphasis on other indicators of the strength of the evidence, as I've laid out. Transparency and open science. So at least one thing that's come out of this debate about replication is that manuscripts need to actually tell the reader enough about the methods so that studies can be replicated. And so there's, as you probably know, an increasing trend to publish, for example, statistical analysis plans also the code you use to analyze the data, and so forth. Publication of study protocols and statistical analysis plans, so specify how you're going to do your analysis before you have the data. Registered research reports is where you submit the method section of your manuscript to a journal before you've collected data, and the journal approves or doesn't approve it, depending on the strength of the method and the interest of the question, before the results are known, so that neither the journal nor the researcher can select for publication results that happen to have a small p-value. So this is to deal with publication bias. There are also various suggestions on improving the design of observational studies, including methods from the causal inference literature, such as emulating the target trial, using directed acyclic graphs to clarify hypothesized causal relationships. And then and triangulation, which is similar. So you don't just trust one study design, but you try to investigate the same question with different methods. And so forth. So there are quite a few things you can do, and all of them lead you beyond, lead you far beyond this this world of where you judge the evidence mainly by how small is my p-value. I would argue that all of these things in themselves probably won't be enough, in the sense that you can't just have a recipe for, okay, instead of statistical significance, then we should do something else. We should, for example, use methods from Bayesian analysis, for example, and evaluate our evidence that way. I would say that no recipe is ever going to get over the fact that the source of the problem is that if statistics are treated as something that gives you certainty, but you actually have to, when you have to do statistics as an hypothesis test, that already means that your data are contain a considerable amount of uncertainty, contain random variation. So here's an argument from Andrew Gelman, who says that a greater acceptance of uncertainty and embracing of variation would be necessary. So papers don't need to claim, yes, we found an effect. They can say we found strong evidence for this, but further studies should check it, for example. And then this is my final slide, where the joke here is the graph is so clear, shows so clearly that vaccines work that you don't need to do statistics. The joke is that, of course, the graph is statistics. The joke is that some people think doing statistics is calculating p-values. So if you don't need a p-value, then it's not really statistics. But actually, the deeper point maybe is if we think about the kind of studies we do, the kind of studies we design, the kind of studies we plan, instead of looking for small p-values potentially for relatively small things, maybe we should look for the kinds of questions where or with kind of study designs that will allow us to really create a stark contrast where we don't need to rely on p-values around the 5% mark to tell us how strong the evidence for or against something is. But that's me. I think the slides will be shared afterwards. So as Tarani very kindly said, I've written 2 books, and the talk is based on a chapter in the Purple Book. But I think these slides will be shared afterwards, and there are references also if you want to look up some of the things I've talked about. But with this, I conclude, and I'm sorry for overrunning considerably. I'll stop sharing for a moment so I can see what's going on.
Thank you so much, Peter. Yes, you are right. The slides will be shared. The recording will be shared on the website as well. So people will be able to access your references and your slides. Thank you so much. That was super interesting, and we have time for questions. So don't worry about overrunning. There's lots of time for questions. People, please, feel free to write your questions in the chat or just unmute yourself and raise your hand. Using the captions, or just physically raise your hand and show yourself. Please don't be shy. Peter has given us a very accessible understanding of the problem with p-values and their interpretation. So he's not a scary person to ask questions about. So please don't feel shy in asking questions. And while you're thinking, I just want to say, Peter, thank you so much. I really enjoyed that. So I've literally just taught my statistics class a few weeks ago, and about significance, and I kept hammering in the point about the p-values are probability statements about the data, not about the hypothesis. But sometimes the students in their assignments keep making some wrong inferences. But it does get me thinking about, why don't we call these kinds of p-values descriptive statistics instead of inferential statistics? They're describing the data. You're making probability statements about the data, and yet we sort of, when we teach statistics, we often talk about them in the inferential statistics parts rather than in the descriptive statistics part. So I don't know. Maybe my suggestion is to say, we're still describing the data when we're talking about p-values, and some people make inferences about whether a hypothesis is likely to be right or wrong, but really it's part of descriptive statistics rather than inferential statistics. That's my controversial idea. I just wanted to.
Right, that's really interesting. May I respond to that straight away?
Sure. Yes.
I mean, I'd firstly say, I teach a lecture also in my statistics class that has some similarities with this talk. But still, let's say that the interpretation of p-values that students then give is not always, well, how I would recommend doing it. But I think it's difficult in education because students also read lots of published scientific papers, and they are, well, doing it wrong or defining it wrong or using formulations that are at least not very careful quite often. So it's quite a difficult habit to break because it keeps getting reinforced. So I don't think anyone has solved the problem of statistics education. Well, how statistics education would need to change for science to improve, especially statistics education to people who are not themselves studying statistics but studying other disciplines, so they don't want to learn all the maths, for example. So that's one. In terms of p-values being descriptive statistics, I think it's really interesting. I think if you like, for example, if you analyze large surveys and like you might use software SPSS or Stata, and you do like large regressions, and you can't even switch them off. By default, you get all these p-values for. You might have a regression with 20 variables. You get p-values for all of them, but actually you don't necessarily need or want p-values for all of them, but you can't switch them off. So there, I'd almost be inclined to agree that they're almost, well, they're certainly not, they certainly shouldn't be interpreted as straightforwardly as indicators of the strength of evidence for anything. So in that sense, I'd agree that they're not really inferential statistics, but they're also not good descriptive statistics, because some people look at them and say, this is therefore important, or this is not important, or actually what people sometimes fail to do is think about what the effect they're estimating actually means. So what would it mean to say that this regression coefficient is 2? What does that mean? Or what does an odds ratio of 1.5 mean? How does that actually translate into the difference it makes for patients or people, whoever you study? And And I think sometimes it's actually the lack of thinking about the real world implications of what you're estimating in terms of the number that leads people to say, p-values, at least I know what to do. I know I have to check whether it's bigger or larger than 0.05. Whereas interpreting odds ratio takes a bit more cognitive effort and might mean that you have to understand the scientific field in which you're working very precisely, and so forth.
Great, thank you. There's a question from Jack in the chat asking about how to responsibly conduct exploratory analysis. Right? So if you're running analysis without any pre-specified hypothesis, is it just a matter of not trusting exploratory results until they're replicated?
Yeah, so I'm certainly not, so that's a really good question. Thanks for that. So yeah, I mean, I'm certainly not saying you shouldn't do exploratory analyses. I mean, that happens all the time. And as I said, I mean, there are entire scientific fields where, if you do secondary analysis as your bread and butter, for example, secondary analysis of surveys, for example, or cohort studies, you never actually have, and some of these data sets you know very well for years, you never actually have the chance to specify your hypotheses before you've seen the data. Yeah, so when you do exploratory analyses, I think one thing to be aware of is that any p-values that you get and that your software might spit out automatically, they don't really mean what they're sometimes thought to mean. So in a sense, strictly speaking, if you do exploratory analyses, you shouldn't report p-values afterwards. You can report what you found, say, I don't know, men and women differ by this much in this data set, and there was a standard error about this big. So you might report something like, well, this seems to indicate there is something to see here, but yes, for a proper replication, for a proper confirmation, you would need to do a different study where you don't know the data yet, but you're having that hypothesis that men and women differ in that way before you start, and then check whether you find it. So yes, so strictly speaking, exploratory analyses won't tell you anything definitive. But that's why I think they're probably best if they're informed by substantive knowledge of the subject area. So you kind of know already a little bit what you're looking for. I don't know whether that answers your question. So I don't have a recipe for doing it. I'm just saying, of course, you should do exploratory analyses, but you should be cautious on what you yourself believe about the results and how you then report them also.
Thank you, Peter. Please don't feel shy to ask questions. You can always write in the chat, and I think Jack just wrote, thank you. So while people are thinking, I just like to say I was devastated to find out that the chocolate and weight loss study was a multiple testing error type study, sadly. But yeah, I love the power posing study as well. That got a lot of attention, and so I just wanted to hear your thoughts about that, Peter. Was it a question that okay, it was a randomized control trial, but was it a problem with the small sample size or sampling, or so what? I mean, here was a p-value that we would normally trust because it's an RCT. But okay, it was close. Was it an issue because it was close to the 5% mark, or was it just a small sample size or a small effect size? Any further thoughts on the original power posing testosterone study?
Yeah, right. So okay, so it was a small study. It's 42 people. One thing that happens in small studies that is kind of obvious once you think it through, but people don't usually think through. If you have a small study and you happen to get a small p-value, it means the effect size you're observing is large. Because to get a small p-value with a small, p-value with a small study, it has to be a large observed effect, so a large difference between, in this case, the power posers group and the other. Now, however large your study is, whether you have 42 people or 100,000 people, you can always get a p-values smaller than 5%, even if the null hypothesis is true. In fact, your chance of getting what they call a statistically significant result for null hypotheses that are true is exactly 5%. So on average, 1 in 20 studies find a type 1 error. That's why multiple testing is problematic. So if you do 20 tests on average, and all of the null hypotheses are true on average, you reject one of them. So with this particular power poser study, there was some indication that they did a little bit of, they had some researcher degrees of freedom in the way they analyzed the data. There was something about, I think, excluding an outlier, which I can't remember in detail. But overall, it was a well-conducted study. I think the problem there was really rather, you sometimes get type 1 errors. You sometimes get small p-values, even if null hypotheses are true, and not because of anything you did wrong, but just because of the laws of chance. So like say, okay, if Tarani or I play the lottery today, we're unlikely to win this next weekend, whenever the draw is. But if several million people play the lottery, the chance of at least one person winning is actually relatively high. So it's similar with hypotheses. In your own study, to get a small p-value, even if your null hypothesis is correct, is not very likely. But in the course of science, because thousands of studies are done every week, there are lots of small p-values in there that are about null hypotheses that are correct, even apart from all the other methodological issues you could consider, as I've said.
Great.
I hope that answers the question. I'm not sure.
Thank you, Peter. We have a few questions in the chat. I don't know if you'd like to read it. There's one from Rui Jiang. A question about the regression-based approach. Approaches might quite easily suffer from p-hacking. What do you think about coming up with more rigorous defined models or metrics to unveil the mechanisms behind? So what can we do to...
Yeah. Right. Thanks for that question. Okay, I've got to try and answer, and you can tell me if it's not what you wanted to know. But I think the fault is not with regression itself. But there could be a problem if you use regression routinely in a way where you say, have one thing you're interested in, say, I don't know, what predicts unemployment? And then you put, say, 20 variables about the people's lives into your regression, and you check which of them predict unemployment or employment. If you do that and you have no prior theory, you haven't thought about which variables are probably important or which variables specifically you want to test, then your research can easily degenerate into just checking, which ones have the small p-values, those are the ones I'll focus on in my interpretation. But if you use regression in a different way and you say, well, I've got a specific hunch I want to test. So for example, I think, and I know this is not a great example for social science, but for example, I think if the parents have a history of unemployment, the children are also likely to be unemployed. This is what I want to test. And then I think very systematically about, okay, what other things do I need to adjust for? What happens if I adjust, for example, for education level? Is this going to interfere with my theory? Like, should I adjust for that? If my theory is right, is the effect of the parents' unemployment on the children's unemployment, should it be adjusted for education, or should it not be adjusted because it's actually on the causal path from the parents' unemployment to the children's unemployment and so forth? So then you get into thinking about doing quite a lot of thinking about your regression model before you actually start. And so the method I reference in one of my slides, direct acyclic graphs, which try to clarify the causal structure between the variables you include in your model before you start modeling. That would be one way to be more systematic about it. So I think it's not so much regression that's at fault if it, if there's fault here, but sometimes the way in which it's used. Yeah. I hope that is an answer. If not, feel free to get back and I'll clarify. But I think there was another question also.
That's right. Yes, there's a question about when you have results from the same data, so the same data being used, but different data analysis methods reveal different inconsistent results. So
right.
What can we do about that?
Okay. Yeah. No, that's an excellent question. I mean, in a sense, it sort of links to it links very well to the problem I described, because I think, okay, there's several things to say. First of all, what do you mean by different? So sometimes, because I've seen sometimes people do the analysis one way, say they use it to do a very simple example, they use a t-test and the p-value is 0.049, and then they use a non-parametric test and the p-value is 0.051. Now, those are only different results if you make a cut at p-value being 5%, smaller than 5%, being statistically significant. But actually, if you look at the p-value as a continuous measure of the strength of the evidence, those two results are almost the same. So that's one thing I would say. So if you judge the difference of results, don't judge it by statistical significance. Look actually at what it suggests about the size of the effect, and if the p-value is actually valid in your case, what the p-value actually is, rather than just whether it's smaller or larger than 5%. Then the other thing is that, of course, getting different results using different analytic methods reveals the sensitivity of results to the methods you use, and the methods you use, they all come with assumptions. So one way to think about methods effects, so different methods getting you different results, would be to think about, well, which assumptions am I making in one method that I'm not making in the other, and vice versa, and which assumptions are plausible. If you don't know, if you can't tell, then one strategy would be to regard it as what they call a sensitivity analysis. So you would say, for example, under assumption A, my conclusion would be that, vitamin X causes, it prevents this sort of disease. But if I don't make those assumptions, then I find that it probably doesn't, or not as much. So I'd recommend other researchers to argue with me about which assumptions are plausible, and to test my result using different methods that maybe don't need to rely on these assumptions I need to make because of the limitations of my data. So these would be the kinds of ways I would think about it.
Great, thank you, Peter. Just to pick up on the last point about sensitivity analysis, you mentioned researcher degrees of freedom, and whenever I think about that, I think, isn't that a fancy way of talking about sensitivity analyses? Are they the same things?
Well, I would say, okay, so I would say researcher degrees of freedom arise when, you've got more than one way of doing your analysis. If you're not aware that this is a problem, you might do the analysis several times and then trust the one that has the result you prefer, or that has the small p-value, and you report it as if you'd just done it that way. And you're not reporting that, in fact, you've done your p-value is invalid because it's subject to having essentially done multiple testing. Sensitivity analysis is when you systematically think through, all right, say, okay, if I can assume that this, to take a really simple example, if I can assume that this variable is normally distributed, even though, in my data, it's unclear whether it actually is, But if I can assume it's normally distributed in the population, I can do a t-test, and that would give me this sort of strength of evidence. But if I can't assume that, and you need to use a different test, non-parametric, say, the evidence might be less strong, for example, or for what I want to show. So the sensitivity analysis would be a systematic way to think through what the meaning of different analyses is, whereas falling into the researcher degrees of freedom trap would be to do the analysis different ways without a clear strategy potentially, and in the end report the thing that shows what you want or that has a small p-value. But yeah, of course, it's a wider topic. But that's the basic distinction I would make.
Great. Thank you, Peter. This final question in the chat about, two more questions, I think. So
Yeah.
would you suggest any toolbox or standard ways to avoid p-hacking for researchers, or detecting p-hacking?
Yeah, so avoiding it yourself, as much as possible, pre-specify your analyses. If you're working in a group, talk that through. Some people don't like it because they have to do more work before before they start to get results. But so, for example, so I work as a statistician. I often work in collaborations. People sometimes tell me they just want the statistical results, but I tell them, well, actually, we need to think about what exactly you want to get out of it, how we're going to do it before we even start. That's going to improve the meaningfulness of any findings we have. So that's one. Detecting it in papers, well, that's difficult, but so I would trust manuscripts more where they show that they have that their investigations are based on a thorough consideration of prior evidence, on thorough consideration of theory. If they show that they have pre-specified the analyses, of course the evidence is stronger. There's some, but yeah, and there's no absolute way to detect p-hacking, I think, in manuscripts. Although I might have to think about that more, whether there might be some other sort of signs that I can't think of now.
Thanks, Peter. Question on control variables.
Right.
Is the main effect, significant main effect, more robust if we control for as many control variables as possible? What kind of control variables should we include?
Right, excellent question. This could almost be another talk. So this p-value thing I've talked about for a bit, and I wonder whether my next hobby horse will be to talk about statistical control or adjustment, because this is another issue that's difficult to understand, I think, and where there's sort of like, say, poor practice going on. So no, you shouldn't. So more control variables are not necessarily better. So statistical adjustment or statistical control needs a causal justification. You might very well control for things and create bias in your in the effect that you actually want to detect rather than improve its estimation. So to take a really simple example, let's say you want to detect the effect of smoking on death from any cause. So your interest is in, does smoking cause people to die, for example, earlier than not smoking? And now imagine you also have data on whether people have lung cancer. So if you do a regression of death on smoking and control for lung cancer, you will what they call over-adjust. You will it will lead to an underestimate of the effect of smoking, because you've adjusted for one of the mechanisms by which smoking causes death. Smoking causes lung cancer causes death. If you adjust for lung cancer in the regression of death on smoking, you'll bias the effect that you want to estimate, which is the effect of smoking. So you need to, and so this is a simple example where we all know the causal relationships, but there might be a lot more subtle ways in which over-adjusting, so adjusting for variables you shouldn't adjust for, can actually bias your result rather than not. So there are a few quite a good papers about that issue on there. If someone's really interested, so I haven't cited them in my talk, but if someone's really interested in this, please write to me and I'll send you the links, or I can send them to Tarani also to share if that's more helpful.
Thank you, Peter. It's a quite a philosophical question here. What if there are some assumptions that you can't test?
Yeah, that happens all the time. You just have to say, someone should test it in the future. Well, okay, so they're different. Well, okay, so they're different things we call assumptions, right? So, there's sometimes the various statistical technical assumptions, such as, this variable follows a normal distribution and so forth, and maybe your sample is too small to convincingly decide whether this is actually a normal distribution in the population. Yeah, in that circumstance, sometimes you have a reasoned choice to make. So, for example, you will go with a more cautious analysis, so the non-parametric one, for example. But sometimes assumptions, of course, are a lot more, are less sort of statistical technical. For example, your assumption might be something like, well, a classic assumption in regression analyses of observation data is there are no unobserved confounders, and you can't strictly test that. So that happens all the time. I mean, I would say almost every time you have an observational study that tries to make a causal claim, you have this untestable assumptions of unobserved confounding. All you can say is, well, my result is only valid if there's no unobserved confounding. But you can do things to further explicate explain the strength of your evidence. So, for example, there's this technique called bias analysis, where one example would be you could mathematically determine how large an effect any unobserved confounder of the relationship of interest would have to have on the outcome in order for the effect you're interested in to disappear after adjustment, as it were. So you kind of check how plausible is it that there is a confounder that has such a large effect on my outcome that the effect I'm estimating would completely disappear. And that might give you a stronger handle on like how plausible the effect you actually found actually is in reality. So, for example, with the vitamin and heart disease study, the odds ratios that were found were quite small, I would say. So it doesn't take much for a confounder that isn't in the model to come along and make that disappear if you had measured it. But some effects, for example, smoking on lung cancer, are so large that even if there are unobserved confounders in all the observational studies that have been done, it's almost impossible to explain away the association between smoking and lung cancer. Even though obviously you don't do a randomized control of smoking or lung cancer, you don't randomize people to smoking, but this effect is so strong that it's pretty clear that it can't be explained away by unobserved confounding. So I guess the general answer is you have to think, what is the assumption I'm actually making? Can I do some technical bits to interrogate it? Or do I have to say, well, further research should do that, or I should do another study to check that assumption, and so forth. Hope that was helpful.
Thank you, Peter. Yes, that was definitely. Perhaps the final question, any suggestions for checking robustness when the sample is not very large? For example, between 100 to 200 N.
Checking robustness. Robustness of what, I guess, is the question. And if the questioner is there is it about robustness of statistical assumptions such as like normal distribution, or what kind of robustness? If the questioner wants to unmute themselves, oh, the result from regression, right? Yeah, but robustness to what? Okay, right. Okay, let me try and answer. Okay, so you have regression with a small sample size. So first of all, the more variables you have in regression, you need to think about kind of not just the sample size you have, but also how many, what's your sample size per parameter you're estimating. So if you have a regression, for example, with 9 variables, 9 explanatory variables, then you're estimating 10 things, 1 intercept and 9 coefficients. And if your sample size is 100, you only have a sample size of 10 per thing you're estimating. So that would be like super small, and it's in many ways that analysis would not be robust. In terms of robustness to assumptions of regression, so for example, normal distribution, or if it's a different type of regression, say Poisson distribution or something like this, there are, of course, methods for getting robust confidence intervals or robust p-values. In some programs, the command to get them is actually called robust, but they're statistically they're called either sandwich estimators or bootstrap methods. So then you are freeing yourself from some of the statistical assumptions that is unclear whether they hold in very small samples. But of course, you're still, in terms of your statistical power to detect effects, to get strong statistical evidence for anything, you're still limited by the small sample size. So in that sense, if you have 200, if your n is 200, your n is 200. There's nothing you can do about it, but you can do something about maybe protecting yourself against making overconfident assumptions about the distributions of the data, and that would be to use what are actually called robust methods of inference. So, for example, robust confidence intervals. I don't know whether that was what you meant by robustness, but yeah. So I increasingly use Bootstrap, for example, in my own analyses, and I think it's becoming more popular to do that.
Thank you so much, Peter. I think we've come to the end now. So all that's left is for me and everybody online to thank Dr. Peter Martin for an excellent seminar. I think hopefully we're all a little bit more enlightened about the uses and misuses of p-values and statistical significance. So thank you so much, Peter, for doing this.
Well, thanks again for the invitation, and thanks to everyone who came and for all your questions. It's actually been great fun to talk with you. And well, for you, I have to wish you a good evening. So I think this is the end of your week, right? So have a good evening. I hope you have something fun or uplifting planned. And for me, I've now got a working day ahead, so I'll be thinking of you relaxing after this seminar.
Thank you so much, Peter. You have a good time too. Thank you. Bye-bye.
Thanks. Bye-bye.